If I give you two vectors and ask you to add those vectors together, do you think you could do it? Like, let's say I give you a vector that is 10 meters to the east, and then I give you another vector that's 5 meters to the east. What's the sum of those vectors? What is it? Remember, to find displacement, we either add displacements or subtract positions. We have two different displacements here. We add them up, right? 10 plus 5 is 15, right? Make sense? The sum of those vectors is 15. This is not crazy hard. This is not meant to trick you yet. But rather, it's just a matter of saying, look, we went 10 to the east, then we went 5 to the east, so our total displacement would be 15 to the east. Okay, does that make sense? All right, well, what about this one? This one's a little bit harder, but you'll still manage. We got 10 meters to the east, and then we have 3 meters to the west. How do we add those guys up? Yeah? Well, we still add them. If we want to add vectors, we still add, right? But we're going to say 10 plus Riley? Yeah, 10 plus negative 3, which is, I mean, that's effective subtracting, right? But we're still thinking of it as adding. So we're going to say 10 plus negative 3 gives me 7 meters to the east. Make sense? This vector addition thing is easy. Man, that's all it gets to, then life is going to be easy today. Well, unfortunately, it gets a little bit harder. What if we give you this one? What if I said 10 meters to the east, and then I said 5 meters to the south? How do we add those guys up? Whew. Well, 10 plus 5 is no longer 15. 10 plus 3 may no longer be 7. 10 plus 5 is 15 in grade 1. 10 plus 5 could be 5 in grade 6 because it depends upon whether it's going right or left, right? Positive or negative. You learn to add negative numbers. But now, the rules of vector addition, 10 plus 5, it's neither 15 nor 5. We learned to add scalars in grade 1, although your grade 1 teacher probably never told you you were adding scalars. You learned to add vectors in 1 dimension in grade 6, although your grade 6 teacher probably never told you that. He or she just said, well, we're going to add 10 plus negative 5 gives me 5. Okay, we learned to add vectors, though, in 1 dimension. Now we're going to learn to add vectors in 2 dimensions. What if we're going to the east, then we're going to the south, or we're going to the north, and then we're going to the west? How do we deal with this? Well, that's what we're going to see as we carry on for the day here. I want to define a reference frame for us here before we go any further, all right? We have 2 axes. There's actually 3 axes. There's an X, a Y, and a Z. But on your paper, there's 2 axes. The right and left axis is our X-axis, and our up and down axis is our Y-axis. Now, the Z-axis would be towards you or away from you, right? We only deal with things in Physics 20 in 2 dimensions. When we learn to do that, however, you could extend that without too much difficulty to 3 dimensions, X, Y, and Z, but we just don't need to do that in Physics 20. Okay, so we'll just deal with the X and the Y axis in Physics 20. Okay, make sense? So anything left, right is X. Anything up, down is the Y component. Now, we have a vector here. We have a vector here that is, actually I should have, before I do that one, I should have drawn another one here. Let's say we've got a vector right here that's 10 meters. How much of that 10 meters is X? How much of it's 10 meters? How much of that 10 meters is X? All of it. Yeah. How much of it's Y? None. How about this one? How much of that one is X? None. 0. How much of it's Y? 5. Good. How about this one? How much of that's X? What is it? Right? Negative 3. Why is it negative 3? because it's to the left. How much of it's y? 0. What about this one? How much of that's x? 0. How much of it's y? -7. You can identify what's x and what's y here, right? What if we see something like this? We got one that's like, say, 10 meters at an angle of, let's say, 30 degrees. How much of that one is x? How much of that one is y? You don't have to answer that question yet. It's kind of rhetorical right now. How much of that 10 meters is x? How much of that 10 meters is y? Well, what we want to do first is identify what is the x component and what is the y component. We're going to label this as x. If we can find this, that's the x component of the 10. Does that make sense? How much of that 10 is x? Well, whatever the blue line is the x component of the 10. How much of it's y? Well, whatever the... I'll just stick with blue here. Stick with the same color, just in case we have anybody that has a little bit of trouble distinguishing colors here. Almost went a different color there. The y component is this. It's our second arrow here, right? How much of it's y? Well, we don't know the number here yet, but if we can find that side of the triangle, then we have the y component. Look, these ones are easy. Just got to be careful with the negatives. The x and y components of the 10, a little bit harder, but if we can find the sides of the triangle, then we can find the x and y components of this one as well. Anybody have any idea how we might go about finding the x and y components of this? Yeah? Yeah, we're going to use a little bit of trigonometry. Sine, cosine, and tan. I'm going to spend just a short time reviewing sine, cos, and tan, because for all of you, it's been at least a year since you've done it. Some of you may not have done it in great detail at all in Math 10. Everybody's done it, but some people do it some classes do it in more detail than others. If you've taken English Math 10, you've done sine, cos, and tan in quite a bit more detail than if you've taken French Math 10. Okay? So just in the interest of making sure that everybody's on the same page, we're going to do a quick little review of that here. Here's a triangle. Here's a theta. We'll make theta 30 degrees. Okay? We're going to label the sides of this triangle right now. Opposite, adjacent, and hypotenuse. 3 sides. Opposite, adjacent, and hypotenuse. Remember this first. The hypotenuse is the longest side. Got it? Hypotenuse is this one. And it is always the longest side. Now, by the way, this only works if you have a right-angled triangle. You guys remember that? If you don't have a right-angled triangle, you can't do this. If you have a right-angled triangle, the longest side is the hypotenuse. Now, we have 2 other sides, the opposite and the adjacent. Which one's the adjacent? The one that's what? The one that's not up? Oh, the one that's not opposite. Okay. So I'm asking, which one's opposite, which one's adjacent? Say, which one's adjacent? Oh, it's the one that's not opposite. Well, you're correct, technically. It is the one that's not opposite. And you could, by that rationale, say the one that is opposite is the one that's not adjacent. But can we clarify just a little bit there, Ronnie?
The one that you mentioned.
Yeah. Here's the way I always think of it. There's 2 sides that touch the angle. There's the adjacent and the hypotenuse that touch the angle. The opposite doesn't touch the angle. Adjacent and hypotenuse touch the angle. The hypotenuse is the longest one. So that means this one must be the adjacent. Does that make sense? Those 2 sides are the ones that touch the angle. One of them is adjacent, one of them is hypotenuse. We know which one's hypotenuse because it's the longest of the 3 sides. The other one has to be adjacent. And that means that the third side here that we don't have labeled is going to have to be the opposite. Does that make sense? Adjacent, hypotenuse touch the angle. Opposite doesn't. The hypotenuse is the longest side. by that reasoning, we should be able to fill in all three sides. Now we have three trig functions that we're going to have to be able to use here. There's sine, cos, and tan. I don't know if you guys remember. I don't know if you guys have learned it this way or not. This is the way that I learned it in high school. I learned a little acronym, SOHCAHTOA. You guys hear that? You guys ever heard that? SOHCAHTOA? SOHCAHTOA. That means that sine theta is equal to opposite over hypotenuse. SOHCAHTOA. Sine, opposite, hypotenuse. SOH.